Okay, thank you, everyone. I think we can start now. Good morning, good afternoon, good evening, everyone. Please let me know if you cannot hear me correctly or anything. Welcome to the Groundwater Youth Network webinar series. This is our 8th webinar, and thank you all for being here. And especially, obviously, thank you to Jayson Gabriel Pinza, who is our speaker today. Jayson is from Bacoor, Philippines. He's bachelor in geology from the University of the Philippines, in Philippines, of course. He holds a joint Erasmus Mundus master degree in groundwater and global change from the Instituto Superior Técnico de Portugal, from Portugal, IHE Delft from the Netherlands, and TU Dresden from Germany. He is currently pursuing a PhD in nature-based solutions to improve groundwater availability in rural areas at the University of Antwerp and KU Leuven from Belgium. He also enjoys swimming, traveling, taking landscape photos, food trips, listening to webinars on groundwater, hydrogeology, and hydrology. And he also supervises Baylor geology students remotely in Philippines, and he also contributes and advocates for science projects remotely in Philippines. He will be speaking on temporal variations of spring hydrochemistry as clues to understand karst systems. So thank you very much, Jayson, and you're welcome. The floor is yours.
Okay, thank you, Gabriela, for the nice introduction. So I'll start the talk now. So here you see a nice picture of a spring in Greece. This is actually the case study that I will present later on. This spring is actually from a karst aquifer, and karst aquifers are relevant worldwide because they occupy 15% of the global land area. In fact, on almost all continents, you can find karst aquifers. Moreover, 10% of the world population depend on it. In other words, we have 10% of the global population who are karst water consumers. So it's really relevant to all of us. But just to be sure that everyone is on the same page, I'll just discuss briefly what karst waters are. So if you have waters that are in a soluble rock, like limestone, gypsum, evaporites, you have karst waters. These waters can flow throughout the pores in between the grains of the rock. It can also flow throughout the fractures and also through the conduits. These karst waters are pristine, like the one you show in the photo. It's really nice, it's very blue, but still, it's vulnerable to pollution, given the growth in population in the world, increasing demands, people messing up with the water quality. So we need to do something about it. The thing is, the vulnerability of a karst system is based on its characteristics. Like, if you know how the fractures and conduits occur in the karst system, that will dictate the vulnerability to pollution. This is to consider that the contaminant can also be transported through fractures and conduits, not just the pores between the grains of the soluble rock. That is why we need to understand how karst systems work in order to manage our water resources properly, considering that each karst system is unique and complex. And one way to do that is we have established an approach, a simple approach that makes use of the most basic hydrochemical variables to understand karst systems. For a brief context of the study, we did this study in the west of Greece. So you see here, we have a highlight here, and that is where the watershed is. This case study, in this case study, we have this Louros watershed, and you can see a large variation in the elevation from 0 to 1900 meters above sea level. In other words, we have a mountainous terrain in this area. And we have a land area of 950 square kilometers, around 2/3 the size of London and Mexico City, and around 1.5 times the size of Metro Manila in the Philippines. This watershed has three karst levels. We have the upper, the middle, and the lower karst levels. And they are separated by faults. And the aquifers here are mostly in the limestone rock. Now, for the hydrochemical investigation that we did, we took some samples from the springs and tried to measure the concentration of the major ions. These ones here are the most common ions found in natural waters. And we also measured some variables in the field, like pH, electrical conductivity or EC, and temperature. We made sure that each karst level is well represented. So we took some samples from the upper, from the middle, and the lower karst level. And we did the sampling every 20 days during the hydrological year 2008 to 2009. So when we say hydrological year, it's the start of the wet season of the previous year, which is 2008, until the start of the next wet season of 2009. Now going to the results. We start first with a bigger picture. So we deal with the karst level. Here, I'm showing you the results of a principal component analysis, more commonly known as PCA, in terms of biplots. So for now just focus on the differences in the colors of these circles here or the plots, which correspond to the individual samples that were collected during the sampling campaign. And what we can see here is that every level has its own cluster. So we can see that the upper level is more or less here, the middle level is here, and the lower level is here. In other words, each karst level has its own unique behavior. Now we try to analyze each karst level. For the upper karst level, we see that the plots occur on the direction of the pH arrow and also on the opposite side of the carbon dioxide, calcium, and bicarbonate arrows. This means that these samples have high pH values but low concentration of the carbon dioxide, calcium, and bicarbonate, which makes sense because the high pH is due to the fact that we have limited carbon dioxide. When we mix carbon dioxide with waters, it becomes more acidic. But this time, because you have not much carbon dioxide, you don't have lower pH, you have higher pH. Moreover, since you have limited carbon dioxide, you have limited dissolution because carbon dioxide promotes dissolution of your rock. So limited dissolution would mean that the electrical conductivity values will also be less. So here I'm showing you the electrical conductivity plots, wherein if you go to the left, you have lower EC or electrical conductivity values. And if you go to the right, you have higher values. For the upper karst level, most of them are actually on the left side, almost closer to the left side, meaning it has lower EC values compared to the other karst levels. And why is it so that we have limited carbon dioxide in this karst level? It's just because we are on a higher elevation, and higher elevation would mean that we can form thinner soil, and also it's relatively cooler there. And it doesn't promote much biological productivity. So less biological productivity, less carbon dioxide, and therefore we have less dissolution of the carbonate rock. But here you see there are some points that I included it. I didn't include it on purpose, and it's because it's a special spring that I will discuss later on. Now I'm going to jump to the lower level first because it's just the opposite of the story of the upper karst level. The points lie on the direction of the calcium, bicarbonate, and carbon dioxide arrows, meaning that it has higher carbon dioxide, which promotes more dissolution, and therefore you have more concentration of this calcium and bicarbonate. Moreover, we are on the lower elevations. We have likely thicker soil that can accumulate, and we can also have more warmer temperatures, and thus we can promote more biological productivity and therefore more carbon dioxide. And that also translates to higher EC as well, because you can see that the plots are somewhat more to the right compared to the ones from the upper karst level where they were more to the left. And then this middle karst level is a bit special because it has other influences aside from the carbonate and the carbon dioxide that influences the overall flow systems. So the other rock units in this Karst level contribute. Like for example, the gypsum that contributes sulfate, and also dolomite that contributes magnesium, and also the magnesium-calcium ratios. But we also have to take note that when you have longer residence time for the groundwater, meaning if you have water that is stored there for a long time, it can also dissolve a bit of magnesium minerals. And that is why we have relatively higher magnesium-calcium ratios as well. So there could be two explanations for this. But both of them can contribute to relatively high EC because you are introducing more ions to the flow systems, more ions, more charges, more electrical conductivity. With this, why do we even care about classifying every Karst level? It's nice to understand how each Karst level would behave and try to relate it with the overall geology of the area in terms of the soil, in terms of the host rock, and also even in terms of the nearby rocks. Now we try to dive into certain individual springs. So I just chose certain springs for the sake of time, starting with this upper Karst level spring, which is U4. And this is the special spring that I was talking about previous slides ago. And it's even special also in the electrical conductivity plots. This is because you see that their values are relatively high for an upper Karst level. Not only high, but even the values are largely spread. But you might wonder why it is largely spread. So it's nice to look what's happening in a hydrological year. So what we do is we try to plot the time series of the hydrochemical variables. So we have the calcium, the bicarbonate, and electrical conductivity. And it's interesting to see that the calcium and bicarbonate are almost coincide, meaning their source is only one, which is the limestone rock. Furthermore, they also have the same trend with electrical conductivity, meaning that limestone dissolution is the most important process that contributes to this flow system's hydrochemistry. Moreover, you see decreases for both calcium and bicarbonate and even electrical conductivity. But what could have been the explanation for this? Perhaps we can try to look at the geologic setting, where if you have water that infiltrates from the recharge zone, since it's recharge period, even the fractures get filled with water. And since flow there is very fast, it bypasses the soil, which is the source of carbon dioxide. It bypasses the soil, and therefore, the water flow systems would not take much carbon dioxide. Less carbon dioxide means less dissolution, and less dissolution would mean less ions. That's why we see these decreases. When we look at the temperature, the spring temperatures decreases quickly. For groundwater temperatures, it's a bit big already if we see this decrease in a short amount of time. And this is decreasing because the recharge period occurred during winters. And it means that the atmosphere and the groundwater flow system is closely linked, or they are coupled, basically. So whatever happens to the atmosphere, if it gets cooler, the groundwater flow system also gets cooler. And it's just because the flow system is relatively shallow enough, so it can experience what's happening in the surface. Going to the recession period, we see the opposite trend. The calcium, bicarbonate, and electrical conductivity are all increasing. And it is because during this time, it's a bit drier, so we do not have much water in the fractures, but we have water that occurs mostly on the pores between the grains. So we have water occurring across the grains, across the pores of the grains, and it's slow. Because it's slow, it has enough time to interact with the soil. And therefore, it can get the carbon dioxide from the soil, and therefore it can dissolve more limestone rock. That's why we see these increases in these ions and even the electrical conductivity. At the same time, the water temperature has significantly increased by a few degrees Celsius. Again, this is big. This is a big increase in temperature for a groundwater flow system. And again, it's just because the flow system is likely shallow enough to experience what's happening on the surface. Again, why do we even care about these technical findings? If we think about the contamination perspective, perhaps how the contamination will occur and it will spread will be different during recharge and recession periods. And perhaps if we want to assess the vulnerability, we should be specific, like how will the vulnerability be during recharge period, or will the vulnerability be during recession periods or dry seasons. Moreover, the shallow depths are also more prone to pollution. Number one, because they are, of course, shallow, so it's easier for the contaminants to reach them. And number two, shallow flow systems are relatively smaller, and therefore they cannot have the dilution capacity to remove the contaminants. So the contaminants can easily accumulate there. So perhaps we need to prioritize on managing these shallow flow systems. Now, let's go to this pair of individual springs, one from the middle Karst level and one from the lower Karst level. Oh, these two springs are from different Karst levels, but why are we talking about them at the same time? If we look at another plot, which is this plot, these scatter plots of the calcium plus magnesium minus bicarbonate versus sulfate, we see that L1, which is the purple one here, and the M1, which is the pink one here, have their clustering parallel to the gypsum dissolution line. And what could be an explanation for this? It could be that we have some mixing with waters that are rich in sulfate. And now what we do is we try to see its time series behavior from recharge to recession periods. But the most striking observation that you can make here is that the electrical conductivity has the same shape as sulfate, not with calcium nor bicarbonate. So it's not the same as the one that we have seen for the U4 spring a while ago. In other words, the changes in the sulfate dictate the overall changes in the hydrochemistry. And therefore, the mixing with sulfate-rich water is relevant in this flow system. Moreover, we see decreases in recharge period and increases during recession periods. And therefore, we see some variation per season. We also see the same pattern with L1 spring, where EC and sulfate have the same shape, same trend during recharge and recession periods. And we also see these decreases during recharge periods and increases during recession periods. Perhaps we're thinking why, or what could have been explanation for this, that they have the same behavior throughout the year. We were thinking that it could be that these two springs or these flow systems contributing to these springs are connected. Even though they're from different Karst levels, it's still possible that their flow systems are still connected. Again, why do we even care about that? If we think about the pollution or contamination perspective, if we mess up with the flow system in the M1, if we introduce a lot of contaminants, perhaps this contamination can spread throughout the flow system all the way to the L1 spring. So we need to think about shared vulnerabilities in the Karst systems. Now, to finish this presentation, I'll just give some summary of what we have done. We only analyze the most basic hydrochemical variables because these variables, you can find them in any natural waters. We also made use of pH, electrical conductivity, and temperature. And we already got something out of these most basic hydrochemical variables. Like we were able to use principal component analysis or PCA and try to relate them with the geology, with the soil, with the carbon dioxide availability, with the host rock, with the nearby rocks. We're also able to understand how the electrical conductivity occurs in a hydrological year here, if it's just closely clustering or if the spread is big, and what could have been explanation for that. We also made use of scatter plots to try to detect some hydrochemical processes such as gypsum dissolution. And we also made use of time series graphs so that we understand what's going on every season, during recharge period or wet season, and during recession period or during dry season. And with this, it's cost effective, and we hope that this can be applied elsewhere in the world, especially with the understudied Karst systems. We hope that we can contribute to this, and we hope that these Karst systems can be better managed if we know the whole story and how the Karst system behaves. And with that, this QR code is for the recently published paper where we based this presentation on. So you feel free to scan it if you want to have access to the article, and also I can also send the DOI in the chat box. And with that, I would like to thank you for listening.
Thank you, Jayson. Thank you very much for that super interesting presentation about Karst aquifers. I'm not very much familiar with that here in Argentina. As I saw the map, we don't have much Karst aquifers here. So thank you very much.
Do you want me to
we have
share
42 attendees.
Do you want me to share do you want me to share the QR code? Like the slide with the QR code? Or
this is the sure. Oh, leave it here. Yes, please leave it here. Thank you.
Yeah.
Thank you very much.
This one, yeah.
We will also send, if you're okay with that and you send us the presentation, we can also send if anyone is interested, we can also send the presentation. And we will, this is being recorded, so we probably also, we will be uploading it in our YouTube channel. So thank you very much. I would like to know if there's any question for Jayson. There is, yes. If you want, there's a question from Clem Kajigal, and I can also put you as panelist if you want, if someone wants to share anything or open their screen or ask something, I can change that. So the question is, hi Jayson, thank you for that interesting presentation. Will the age of the karstic limestones or its age of karstification, if it's young or mature relative to surrounding lithologists, have an effect in the trends that you have mentioned?
Yes. Yes, especially that if you have older limestones, probably have likely more magnesium that can be incorporated in the flow systems. So the answer is yes, especially that the very old limestones can have magnesium minerals. And some of them could be even dolomitized. Yeah, it's a bit tongue twister. So you can have more magnesium calcium ratios and also magnesium. So yeah, it can affect the results.
Great. Also another question from an anonymous attendee says, I might have missed it, but what is the average recharge rate of karst aquifers?
Oh,
an average recharge rate.
Average recharge rate. That's a bit tricky question because I'm not sure if he's talking about karst aquifers in this study area or is it like in general?
In general.
Because in general.
No, I don't know. I don't know.
Yeah, I'll try to answer, but I don't know the answer to be honest, because I didn't really focus much on the recharge rates. But in general, I think it's also a bit tricky because knowing that karst aquifers have different behavior during recharge and recession periods, it's a bit tricky to identify, especially if you don't know if all the conduits will contribute or only certain ones. It's a bit tricky to get a good estimate. Although there's a method for Mediterranean karst systems, but I forgot the name of that method. But yeah, there's a method to estimate that. That is a very rough method that can be used to estimate it. So yeah.
Thank you. There's another question from Merit Ekis. How did he decide there are only 3 clusters? Just visual inspection?
We already have an idea of the general geology of the area where we have the 3 karst levels. We already know it from the start. So we use that as a basis for the clustering.
Okay. Clarice Ishmewe says, hi Jayson, do you think land use across karst level can affect the hydrochemistry of karsts?
Yes, definitely. It can affect. It depends on which land use. For example, agriculture, perhaps you can introduce more nitrate and it can affect sometimes if it has too much nitrate, nitrate becomes a major ion. That can happen. And also if you have industrial or residential areas where you have wastewaters, these wastewaters can also infiltrate the closed systems, and it can also introduce contaminants as well.
Yes, I was going to ask you, since we'll see if there's another question there, but I wanted to ask you about a little bit about the context of this area, and what are the main pollution sources or land uses that could contaminate this area. Can you
It's a pristine area. So the land uses there, they have some agriculture in the lower Karst levels, but it's not too much to contribute the nitrate there, for example. So relatively it's still unpolluted.
Oh, good.
Yeah.
Great.
But of course, even if it's unpolluted, we need to prepare ahead of time and how we should manage it more effectively. Yeah.
Sure. Here in the chat, there's another question. Thank you for the presentation. Did you use other methods, for example, isotopes, as a complementary tool to map the aquifer? Nice to see you. Okay, with
for the
from Ghana.
isotopes.
Sorry, I didn't understand this, but
no, I understand. Yeah, it's okay. I understood the question.
okay.
For the isotopes, I didn't include it in the publication, but for my master's thesis, I included it just to understand how, like, just to verify if it's really shallow or deep. Because if it's shallow, then probably there's still evaporation that can also affect the isotope signatures. And also, we also use isotopes to estimate or try to roughly locate the recharge zone, because we have this recharge line where you plot the altitude of the area, the altitude of the area versus the isotope, and I was able to use those plots to at least know where the recharge zone would be. So I use it, but I didn't include it in the publication. So it's mainly oxygen isotopes that I use for this study. Oxygen 18, yeah.
Great. Is there any other question related to the Abe? Let me see. Thanks for your response. Clarice says, maybe I will reach out inbox and to discuss. I'm working with NO3 and EC in Karst in Spring. Karst Spring in France, sorry.
You're welcome to reach out to me. I hope I could help you with that. Yeah.
Oh, there's another question is, what's the economic importance of Karst systems? A difficult question, right?
It's a broad question, I would say. But yeah, I think I'll just go back to the introduction where we see that Karst waters are 10% of the global population rely on it. So
it's a lot.
It's already a lot, yeah. And it occurs everywhere in the world. Like every continent more or less has Karst aquifers.
Do you know that? Sorry to ask you this question. I don't know. Maybe you don't know, and it's fine. From the whole groundwater that is available, aquifer that is water that is available, like 30% of water is from aquifers. How much of that is Karst aquifers? Do you know, from the total of the?
You mean the volume of the water?
Yes. Like
Honestly,
no, it's fine. Don't worry.
Honestly, I don't know.
You mentioned that there's 10% of the population is a lot, right? Of the global population.
I just know that the Karst aquifers would occupy 15% of the world land area, the ice-free, or the ice-free ones. Yeah, that's all I know.
Yeah. Great. And there's another question regarding to the certificates of attendance. We won't provide certificates for the participants today at this event. We will provide a certificate for Jayson, who is a speaker. So I will also invite you to join as a speaker If you want to share some results of your of any paper, any research article that you're working on or that has been published, or your master's thesis or your PhD thesis, you're invited to to join as a speaker. I will leave here the contact in case you're interested. I think I didn't present myself, but I am Gabriela Calderon, and I am part of the network and head of the project coordination committee at the moment, and also have been part of the scientific committee. This webinar series are part of the scientific committee, one of the working groups of the scientific committee. So and we have been doing these webinars since last year. And Georgia Williams, who couldn't be here today, she's the one who is in charge of this working group. So if you want to also be a speaker, you will receive a certificate as a speaker, not as attendee this time. So, but thank you anyways. And in case there are, I would like to also share our link tree in case you are not familiar with our network and you want to join. So you will find there a lot of links related to the Groundwater Youth Network and where you can join. So any other question? Congratulations, Mr. Pinza. I hope you can extend the study here in the Philippines, and you can help preserve our resources, someone from the Philippines. And will this presentation be made available after the webinar on some websites? Yes, it is being recorded, and the idea is to upload it in our YouTube channel. And so here at this link, you can also find our YouTube channel, social media, and yes, I don't know if anyone wants to say something or ask something. Please feel free. This is the moment. And if not, thank you very much, Jayson. Congratulations for the super interesting presentation, and share the YouTube channel. Yes, we will send an email to the participants and with the presentation. And yes, I think there are no more questions. Just we will. There's the link in the link tree. If you enter the link tree, I think there's the YouTube channel is also you can find it there. No, it's not there. I will send sorry. Before we leave, I will just share the YouTube channel because I don't think it's in the, because someone is asking, and we will have some time to obviously edit the video, so please be patient and we will.
There was
you will
a question.
find.
There's a very recent, like a just question that popped up now about the software I used.
Yes.
Maybe for the statistical analysis. I just use R, like the R programming, and perform PCA, principal component analysis there, and generated the plots there. But of course, for the distribution plots, like what you've seen for the electrical conductivity, you can also use box plots. I just didn't use box plots because I wanted to have something that's more visually clear than box plots. But you can actually use Excel even for that. But for the principal component analysis, there are other statistical software. But for me, I just use R. That's the
They're
programming.
asking if
More coding.
ESPSS instead of
SPSS,
R.
yes. Yes, SPSS is possible. Yeah. Any statistical software that can do PCA is possible. Even with for the geologists or paleontologists is past PAST. Past, you can also use that because I was trying that as for fun. It produced the same outputs. Yeah, so it's also possible.
Great.
Especially if you're not really fan of coding. Yeah, I understand. But although you have ChatGPT to help you, to help you generate the codes. Yeah.
Sure. Okay.
Mm.
PCA available in Origin Pro software.
Yeah, Origin
Great.
Pro. I think Origin is also, yeah, I heard of it. It's also famous, but I never use it myself.
Mm-hmm.
Mm.
Great. So thank you very much, Jayson. Please, if you're interested in being a presenter or a speaker at the webinar series, contact us.
Ah.
And yes, we will be in contact then. See you soon.
See you. Yeah.
Bye.
Bye-bye.